Hello and welcome to this course on computer architecture. My name is Bhaskaran Raman and I am with the Department of Computer Science at IIT Bombay. In this introductory video, we will first look at what computer architecture is and why the study of this subject is important. So let us start with what is computer architecture. What does the term architecture mean to you? The term architecture usually refers to a way of designing or making things. Typically, it refers to buildings. So what does the term computer architecture mean then? Computer architecture refers to the way of building computers, the way the hardware and software are put together, the way they interact with one another, and the internal structure of the microprocessor. Before we can learn various aspects of design of computer systems, there are some prerequisites. You need to know some basics of data structures such as arrays, pointers, stacks and queues, and algorithms involving these data structures. You also need to have done a course on logic design, which covers basics of switching theory, Boolean algebra, representation of numbers in computers, and arithmetic involving these representations. Building logic circuits using gates, combinatorial or combinational logic, Carnot maps for optimizing these combinational logic, Moore machines and Mealy machines, finite state machines, constructing them in hardware, using them to make control units, and the design of computer hardware for doing computer arithmetic. These are the contents of this course. We will learn about computer organization, the basic parts of a computer, the von Neumann architecture. We will then look at the design of the instruction set which defines a computer. We will learn about ways of measuring performance so that we can answer design questions in a quantitative fashion. The microprocessor which implements the instruction set has to be implemented in hardware, and this involves the design of data path and control path. We will learn about these. Pipelining is a mechanism to make the implementation of the processor fast. We will look at pipelining methods and the problems we run into in terms of hazards when we try to implement pipelining, and we will also learn ways of getting around these hazards. The next important part of a computer is the memory system. We will look at the memory hierarchy, the design of cache systems, and how the various design choices affect the performance of the cache. We will then look at secondary storage or disk storage and RAID systems which use redundancy to achieve fault tolerance. We will look at Hamming codes as a way of error correction codes in stored data. Then we will look at input-output systems and buses. It's useful to know how the contents of this course relates to the contents of other courses. Here in this diagram, I have shown a hierarchy. At the lowest level of the hierarchy, we have digital gates and circuits using these gates. These are used to implement the various components of a computer, such as the central processing unit or the microprocessor, its memory system and I/O systems. The instruction set of the processor is what is implemented by the components of the computer system. Using the instruction set, the operating system runs, and also the application programs via the operating system use the instruction set to run their applications. If you look at the hierarchy to the left here, the application programs and operating systems are usually written in higher level language such as C or C++ or Java. This higher level language gets converted into assembly language, which essentially corresponds to the instruction set of the computer. The assembly language gets converted to machine language, which is nothing but a binary version of the assembly language, and the machine language is in turn implemented using the digital logic. The lowest level in this hierarchy is typically covered in a separate course which may go by the title of digital logic design. There is typically a separate course to deal with operating system design, and application programs are usually dealt with in algorithms related courses. There is typically a separate course which teaches techniques for converting the higher level language into assembly language. That would be in a compiler's course. This course, computer architecture, deals with these two parts of this hierarchy, the computer system design and the instruction set design. We deal with assembly language and machine language. In this hierarchy, until here is the hardware and above this is the software, and this course will deal with the interface between the hardware and the software. These are the textbook references for this course. I will mostly be following the Computer Organization and Design book by Patterson and Hennessy. I will closely follow the 3rd edition, although it is also okay if you have the 5th edition with you. Note that the 4th edition uses the ARM processor for various examples. The 3rd and 5th editions use the MIPS processor, which is what I will be using. So try to use either the 3rd edition or the 5th edition for this particular course. An additional reference is this book by John Hayes, Computer Architecture and Organization. Note that both these books, there are low price editions available as well as ebooks. Please buy them if you need and don't use pirated copies. I will also be using some notes from other computer architecture courses. So having looked at what computer architecture is and what we are going to learn in this course, before actually learning that, let's first look at why we need to learn these aspects about computer architecture. So take a pause and think why this subject is important, or maybe you think it's unimportant. Let's identify the various aspects of computer architecture around you. If you're watching this video, you're already using computer architecture quite heavily. You're probably watching this on your personal device like laptop or tablet. There are many more components involved as the contents of this video are streaming towards you. The server which is hosting the content and the network routers and switches in between. All of these are computing devices in one way, shape or form. You would have likely used a whole range of personal devices, maybe non-smartphones, smartphones, tablets, laptops. It's actually quite a continuum of devices from mobile phones to desktops, representing a range of personal computing devices. And then there is a whole set of computing and data storage platforms which you actually use but don't interact with directly. These are the servers and data centers or cloud computing platforms which host various internet services, popular ones such as Google or Facebook or Flipkart, Amazon, Yahoo, and so on. These form the backbone of these major internet services. A large set of high power computing devices, computing servers put together in a system called a supercomputer is often used in very specialized but very important applications, weather prediction being one of them, or research applications such as the Human Genome Project, mapping the genes in the human DNA, or other things such as simulation studies of subatomic particles in physics, or research related to climate change involving huge amount of computations of geological models. Supercomputers are used for such research applications and are often points of pride involving national and international reputation. And then we have computer architecture playing a role in what are known as embedded computers. These are very large in number and they are very small that we don't often notice them, but they play very critical roles. Microprocessors are used extensively in home electronic products and in vehicles, and also very extensively in industry automation. So that is with respect to computing devices in various contexts. What about the number of personal computing devices? This graph here shows the number of personal computing devices of various kinds which enter the market per year. This is based on a study done by Gartner in April 2013. So what you can see is that per year there are over 2 billion devices which enter the market, getting close to 3 billion in 2017 is the prediction. The other thing you can see in this graph is that traditional personal computers in terms of desktops and notebooks are actually reducing in number, while its place is taken up by tablets. The range of things for which we are using computing has been growing in large part due to the growth in the raw processing power. In the textbook, there is this graph which shows the processing power in the y-axis, and in the x-axis is time in years. And what it shows, the details are in the textbook, what it shows is that there has been an exponential growth. So the y-axis is logarithmic. So a linear representation in this graph shows exponential growth in processing power with time. It shows that between about 1986 till about 2002, the growth has been about 50% per year. This roughly translates to doubling of processing power every 2 years. And after 2002, it has the rate of growth has slowed down, but still it is exponential. It has come down to about 20% per year. So in this course, we will learn some of the architectural techniques which has driven this kind of growth in performance over this duration, and also reasons for why this has slowed down in the recent past. The exponential growth in processing power has been driven by exponential growth in another metric, and this phenomenon goes by the name of Moore's law. So you can look up graph for Moore's law on Wikipedia, and it will show again a y-axis which is logarithmic, and here it shows the number of transistors per chip, and again x-axis over time, and you will see a linear graph which represents an exponential growth in the number of transistors or the number of gates per chip which has been possible. This exponential growth has also been roughly of the order of doubling every 2 years. So the more transistors we've been able to pack, we've been able to grow the processing power roughly corresponding to that. So hopefully now the answer to the question why study computer architecture is self-evident. Computing is central to today's information age. Computer systems range all the way from very small in devices surrounding us which we use but we don't realize, to personal computing devices which we actually use and experience, and then at the other end we have these high-end servers and supercomputers which also perform important functionalities. New computing devices have been coming up, new end-user devices have been coming up. In this course, we will understand how these various computing platforms are designed, what affects their performance, how we can go about designing these computer systems to optimize performance along various optimization metrics.